All right, I'm gonna I'm gonna get started here, but if anyone needs more time by the time that we get to the actual coding part, let me know and I can give you another moment here. Okay, so today our goal is gonna be to conduct yield spatial temporal variability or stability analysis. Um, I'm assuming that you all have at least taken a look at the paper since it is due tonight. And we're going to be talking about some of the ways that we can, I guess, incorporate yield stability for time and space in this exercise. And we're going to do that for the 3 years of data that we have. So just as a quick refresher here, what we're doing is just a follow-up on the steps that we started, right? So we got the raw yield data from 3 years, we wrangled, we cleaned, and then we interpolated them. And now we're going to combine that final interpolated product of all 3 years into a yield spatial temporal stability analysis. So as I'm sure you've read through the paper already, our goal here is to understand if there are areas of this field that are consistently high yielding or consistently low yielding or medium yielding, but also if they're inconsistent, which is probably one of the most interesting ones. Because if it is inconsistent, there's from year to year, there's probably an interaction between soils and, probably soil and weather. There's probably something going on there related to that, that in one year makes that part of the field being high yielding, other year makes it being low yielding. So we just want to explore that and use that to guide our management creation zones in this field. All right, so our learning objectives here are going to be to import the interpolated clean yield data for the 3 years. So remember that we did all that process for the 2017 year in class, and you did as part of the assignments, the 2019, 2020 on your side. So we're going to import that now and then create the year-specific spatial yield stability areas first. So we're going to go into each one of these years and then standardize things, normalize things, so we can know within that year what was the variability of yield in a standardized way, and then combining those 3 standardized year-specific maps into one map that's going to be our spatial temporal stability analysis. And then we want to export that layer as well as the end of the exercise. All right, so we're going to get to the coding part. If anyone needs more time, please let me know. Otherwise, I'm going to keep moving. I left you all the packages there. I believe you have all of them already, so it's an easy run chunk. The immediate next thing here that you're actually going to help me with is to import the yield interpolated maps, right? So the first object here is going to be the interpolated yield map for 2017. If you followed my suggestion of, well, I guess this one we did in class, so you probably follow what we did in class. So we're gonna give the assignment symbol here. Let's use the function read_sf. Remember, we're using sf here because that yield interpolated map is I think we did a .geojson, but it is a vector shape or a vector spatial file. So read sf for that. Open and close quotation marks. We do it .. to get outside of code. If you hit tab, you can go in, I believe we exported to data. Let's see. Yeah, so in the data folder, we want to bring in the EO17_interpolated.geojson. That's the one that we need. Make sure you do bring the interpolated one and not the clean one or not the rank, or I think we had clean and process, none of those, right? Those have already been through the system and now we're working with the interpolated version. So if we bring that in and you print it, in my case, I have 4,046 number of observations. So this is a simple feature object. It is already projected in UTM zone 16 north. So it is already in meters. All good. Just getting a quick summary here. We just get basically this object has 2 columns. One is yield interpolated in pounds per acre. The other is geometry. We see here the range of yield. It looks good. Nothing too alarming here. All right, we're going to do the same thing for the 2019 one. So read SF, open and close quotation marks, dot forward slash, go inside data, and you should look for the EO19 underscore interpolated. This is the one that you created. So maybe when you created, I hope that you save in the right folder, or not in the right folder, but in the one that we were using in class as well. If you did not, then you're gonna have to look for where you save this in your site, but it should be in the data folder of the 007 EOMonitor project. Similarly, if we just print that, it's gonna be an SF object, projected UTM zone 16 north. In my side, 4,046 rows. This is, on your side, it could be different because this is if you remember, well, let me just, I guess, stop for one quick moment here and ask the following. Why is my EO17 and EO19, why do they have the same number of rows? So 4,046. So on my side, on yours, they should both have the same number, but it could be a different number. But on my side, both of them have 4,046 rows. Why is that? Why is that matching? Okay, it's related to the boundary, but what else? So
They use the same AB line plan, same field, maybe.
Okay, so we're all getting to the idea. But if you think about it, they all had the same AB line, they all had the same boundary, but when we're looking at the yield data points, they had different number of points. So why now do we have the same number of observations across different years on the interpolated map?
Maybe because we use the same digitized map.
Okay, so it's getting to that. So we digitize the boundary, right? So it is related to the boundary. Well, let me go ahead and tell you. We have the same number of observations, and you should on your side as well. They should match on your side, even though yours may be different from mine. Because this is the interpolated, and it is interpolated, so we use the same grid to interpolate. The 4,046 rows are each one of the cells of the grid, right? So now, even though the underlying EO data had different number of points across years, but when we interpolate it to the same grid, they should have the same number of rows because it is the same grid, right? So that's why in my case here, my grid had 4,046 cells that became polygons once we transformed that from raster to vector. On your side, even though this 4,046 can be a different number, but it should match across the 3 different years. So if they don't, something happened and you're gonna have issues moving forward. We can address that later if that is your case, but they should match, all 3 should match. So let's go ahead and bring the EO20. So same thing, read SF, open and close quotation marks, get outside of code, go inside of data. I want EO19 interpolated.gfase. And then a quick check here, we can print it. It's again an SF object as we wish it would be. In my case, again, it matches the same number of rows, which it should do. Check on your side that it also, all 3 of your layers have the same number of rows, even though they may be different from my number here. It is also projected UTM, and we can get a summary just to look into that. So here also we see that it's varying, the yield, the interpolated yield is within a range that is biologically possible, so no errors there. I guess I forgot to check the summary of EO19, so I'm just gonna go back up and do that. So here's as well, we have a very high yielding point, but most of them are within, still within like a similar range to the others. So, here's some quick questions for us to just think through this. So what year was the highest yielding? I guess we can think about this in a couple different ways. One would be looking at the mean, the other one would be looking at the maximum value. I guess if we look at the mean, so 2020 was 1,100. 2019 was 1,600. and 2017 was 1,200. So I guess 2019 was the highest yielding year. The lowest yielding was 2020, right? And then here's again, that question is same number of observations for all layers, but why is that? So it is because this is the interpolated map or interpolated layer that we interpolated to the same grid size, right? Now, regardless of how many points were underlying on that yield, actual yield data point, they would have been interpolated to the same grid size, so therefore same number of rows. All right, so every time that you were going to have different yield monitor data across different years, perhaps different sites, different crops, there will be challenges, right? So one example would be if you have let's say a peanut cotton rotation, or maybe a corn soybean rotation, or any mix of that. You can understand that the magnitude of yield from one crop to the next can be different, right? So you would expect to have a different magnitude for soybeans compared to corn, for example. We're going to have a lot more biomass coming from corn just because that's how it grows. That's the potential of creating biomass that is larger. So, that just tells us that if I just put the actual pounds per acre or whatever unit we have side by side across different years, especially different crops, that is not going to be it's not going to compare well because we have the magnitude of the crop being an effect there. And even if you have the same field but different years, and that's definitely true across different sites, or across different fields, but even if within the same field in different years, we have to find a way to standardize these to compare. So a couple of solutions here and maybe you saw one in that paper that's going to be the first one here. So one of them would be to standardize by the mean, median, or maximum value. This is very common, right? So perhaps it's one of the most common ways. For example, what do I mean by that? I go to each one of those years. So let's think about 2017 first. For all of my 4,046 cells, I calculate them, let's say the mean or the median or the maximum value across all of that site on that year only. And then I use that amount to standardize everything else. So let's say that the median here, I guess in this example, I'm just giving a mean actually of 1,500 pounds per acre. So I take that mean that was calculated for that year only for that crop, and then I divide all the values by that mean, right? So now we're standardizing by the mean, which is going to put all of our values now, instead of having yield, is going to be, let's say, ranging somewhere from 0.6 to 1.8, like just an arbitrary. It doesn't have to be those bounds, but just as an example. So now we have a relative yield terms relative to the mean of that year. And just a quick piece of information for us to think about it. If we standardize by the mean or the median, values would range from, let's say, 0 to about 2, right? And in the middle, the values that are 1 is because they're exactly equal to the mean or the median, right? So it's centered on 1, but it's ranging from 0 to 2, let's say. However, if we standardize by the maximum value, now imagine you go to that interpolated map and you get whatever was the max yield value and you standardize everything by that. Now your values are bounded at 1 because there's not going to be any value greater than the maximum, right? So if a value is equal to the maximum, it's going to be 1, but if it's less than the maximum, it's going to be less than that. So it's going to be between 0 and 1. So different ways of standardizing this, just so you are familiar. These would be on a way, the one that we just talked about would be standardization that your standardized value remains numerical. So remains a number that can range from, let's say, 0 to 2 or 0 to 1, depending on what you standardize by. That is the first method. The second method, which you did not see in your paper, would be to standardize by quantile, which turns your output map into a categorical map, because now we don't have numbers anymore, it's categories. So what we would do is, for example, you take, I guess here is very, very easy example. So you would go to this field this year, you take, let's say, the median, which is the 50th quintile. Let's say the median was, I guess, in this case, 2,000 pounds per acre. So everything that's less than the median, I call that low yielding. Everything that's greater than the median, I call it high yielding. In a way that now my map is going to be the value in each one of the cells is not a number anymore, it's just a class where it could be one of high yielding or low yielding, right? So it's a binary way of creating that in transforming a categorical variable instead. Because now you can think that the median may be different for different crops, different sites, different years, and that's okay. But I'm always using the median specific to that year to say if it's less than the median, it's low yielding. If it's more than the median, it's high yielding. And that way standardizing as well. So the first example here would be standardizing and having a numerical output of that standardization. The second one is having a categorical output of that standardization. In our case here, we're going to use the numerical approach. So for that, I want to standardize by the median, which means that the first step here would be for each one of these years, we need to calculate first the median and then divide everything else by that value. So that's what we're going to do next year for the 2017 data set. I guess before we code, any questions about this quick discussion about methods of standardization? All right, I don't hear anything, so let's keep moving. If you come here in the next chunk, let's give it the assignment symbol. Because we're doing this for the 2017 year first, we need to call that object that we imported above. So that's called yield IC17. Let's give it a pipe. And the first thing I want to give it here is to calculate the median. What can somebody give me a hint here of what function would you use for that? What should we first type here? So my goal is going to be to have a column here that's going to have the median value repeated for everything running down. Any guesses?
Mutate.
Can you repeat that?
You can say mutate.
Yeah, mutate, right? So say mutate. I want to call this median. Let's see what I have here. Median yield underscore LBAC for pound per acre. All right. So I don't know, I think we've seen this before, but there's a function called median that we just give the column that we want the median of. So the column is IP yield pound per acre. That's the current column in our data set. All right, so if we run this and we print it just to inspect what's going on, notice what happened. We have, oops, I guess it's not showing here. We have a new column called median yield pound per acre, where the same value is being repeated for every row in this data set, which is what we wanted, right? So we still have the IP yield pound per acre, which is changing depending on the interpolated value that was calculated. But now we have another column of median yield. That's the same for all the cells because there's only one median for this field. I want to show you something very quickly here. So every time I want to calculate a summary statistics number from a given column, and I want to have that as a new column and just repeat the values down that column, I use mutate. If I just wanted to know what was the median of this data set and just get a number back, I would just do a summarize instead of mutate. You don't have to do it on your side. I'm just going to do it on mine so you can see it. If I do a summarize, I get a summary, right? So I just get that one number. Sometimes summarize is what we want. Sometimes mutate is what we want. Depends on the goal. In our case, mutate is what we want because I do want to repeat that value for all the other cells in this data frame. Okay, so we have the interpolated yield, we have the median yield. Now let's standardize this. So let's use a pipe. Let me ask someone else here. What would you, so given the variables you're seeing in front of you, what code would you type to get the standardized yield when standardized by the median? Neva, what do you think? So given what we're seeing here, right? So we have the median in this column, we have the actual yield value in this column. What would you type here? What code do we need to calculate the standardization value? Have to divide, right? But I mean, I cannot just come and divide, right? I have to type a function here. What function do we need here?
Uh, can I say deploy a select?
Okay, so that's Kumar, right?
Yeah.
Kumar, deploy select would be to select a whole column, but
Yeah.
not to do any operation with it, right? So in this case, it would not be deploy select. So let me help you all. We need a mutate, right? Because they're gonna create a new column. And I wanna, so first thing we give the new column name, I wanna call it SY for standardized yield, keep it short and simple. Now here, Neva, maybe you can tell me what you were thinking, because this is what we're gonna do the division, right? Okay, so IP yield pound per acre. / then median, right? Yes. So yeah, Neva said we take the yield and divide that by the median yield. That's exactly right. If we run that and just print it, we're gonna have this new column here, which now again is it's standardized by the median. So we would expect values to range between somewhere between 0.5 and to 1.8, sort of. Those are just rough guidelines. We see here that we have a whole bunch of them near 1, at least for now. Okay, so a couple of things I want to do here. So I do want to multiply this by 100, so we get like a percent type of score rather than a fraction. So let's just do times 100. And also something that I want to fix here is I really don't care for all these decimal points here. I really just need like 91 point, in this case would be 0.1, we round to 1. So I just want to round this. To do that, we're going to come here and use, so right before IP yield, there's a function called round, where the first argument is what you want to round. So it's still all of this as the first argument. You can come before that closing parentheses, give it a comma. And here is the second argument for the round, which I want to say 1, so 1 decimal point. If you want more, that's what you can change there. And then the parenthesis that was there already now is closing the round function. Make sure you add another one to close the mutate as well. So if you run that and you have your commas and parentheses in the right place, now we should have something like this. Again, in your case, these values are going to be slightly different because you have a different number of cells, which may have caused your median to be slightly different. But it should still be somewhat similar. Okay, and now lastly, I just want to keep the columns standardized yield and the geometry. So now, Kumar, let's add a pipe here, and now we call the select, right? So if I just want to select some columns, that's what select is for. So let's call dplyr column selects. I want to select the SY column, but I want to also rename it while selecting it. So you can type SY and you come before it and then you rename it. So I want to rename it to SY17. So it should look like this, SY17 equals to SY, and then the geometry. That's all I need. So if you run that, this is what you should have now. So the same number of rows, we did not mess with rows. We just created some columns and then selected those columns as well. Just a quick check here. We can do a summary of this object sy_17, just so we can have an idea of sy. So we see here that standardized yield is ranging from 24% of the median to 156% of the median, which would be similar to 0.2 to 1.56, right? We just multiply by 100. That's why these are now our percents rather than a fraction. All right. Let's keep moving here. So next thing is let's visualize this. I want to make a map so we can see what's going on. So I left you part of the code there. Let's just give it the assignment symbol. I want to call it ggplot. I want to leave that ggplot empty at that level, so we can just add a plus. To add the cells of this map, we're going to use geom_sf, right? Because it is an SF object. So geom_sf, I want to say what's the data coming in. So data equals to the sy_17. That's the data set we created above. I want to give it a comma and then call the AES function so we can change the field. I want the field to be according to, so the sy_17 is the data frame. If I print it, I have a column called sy17 without the underscore in it. So I want the field to be according to that sy17. I come outside of the AES and I just want to say comma, color equals to NA. So those polygons don't have an outline. If you run that and you print it, you should see something similar to this. So we're going to do a little bit more of customization this time around, and then we'll just recycle this code for the next years as well. So a couple of things I want to do here. I want to change, I don't like this color here. I want to use something that is going to be interesting for us to talk about. So now our yield is standardized by the median. So we have a middle point here that's basically the 100. So the 100 would be points equal to the mean, or the median in this case, sorry. Values lower than 100 are less than the median. Values greater than 100 are more than the median, right? So I want to use this information that we have a center point around 100 and use that to color our maps accordingly. All right, so come back to the code. We're going to give it a plus here. We're going to use a function called scale_fill_gradient2. So what this is basically, so we're using scale fill because our aesthetics being changed is the fill. If this were the color or something else, it would be scale color or something else. Gradient2 is this scale that we can give it a low color, a midpoint color, and a high color. And that's what we're going to do next. For our low color, you're going to see, well, you know what? Let me see if I just run this, what happens. Okay, so you can kind of see the default is giving the high color is purple, the low color I think is white, and I'm not sure what's the midpoint. I don't think it has chosen one for us. I want to change that a little bit. So it has an argument called low. So here we give the color of what I want to be low. In my case here, I type the hex number of the color, which is another way of referring to a color. I want to give you the hex code I have here. So it's a £, and then 440154FF. That turns into this purple color. That's the hex code of this specific color. You can give it a comma. It has an argument called mid. So mid would be the color I want the midpoint to be. open and close quotation marks. We can just type the name of this color, which is white. And then it has a high argument, which is the color that I want for the high points of this scale, which again, I'm going to give you a hex code. So make sure you type the hashtag, and then the code is 22A884FF. So it should be this like green type of color. All right, if we just go ahead and run that and inspect it, this is what we get. So what's happening here is I don't know what is the actual value on the yield scale that is assuming to be the midpoint, but it's probably something lower than 40 here because I'm not even seeing the purple. For us to tell it what is the midpoint in terms of the value of that scale, give it a comma, and it has this argument called midpoint. We're going to say midpoint equals 100. So again, 100, because if a point is 100, then it is exactly the same as the median. And that's what we want to give it. So now if we print that, this is what we see. So everything that's white is because it's very similar to the median. Everything that is purple is lower than the median. Everything that's green is greater than the median. So an easy way for us to visualize that. You know, we could have, I guess we could have used like a low being red and high being green and still having white as the midpoint. Although that's not a very colorblind safe scale to use. So that's why we're using this one. Also, the last thing I want to do here in this function is I want to tell it what are the breakpoints I want to see here. So I would really just want to see 0 would be the midpoint, 180 and 20, because those are the max and the minimum. So we can come here inside a scale, fill gradients, give it a comma. We're going to call this function or this argument called breaks, or is actually going to be a sequence between those. So we use the function to say starting at 0, ending at 120 at every 20. So this is what we get, and I just want to pull up to the code again in case someone is still catching up. All right.
Can you?
Yeah.
Can you please explain the midpoint section once again? Why we did that? It was not automatically before. Can you please explain me?
Yeah, so I don't know how it calculates the midpoint, the default midpoint value, but it's not what we wanted, right? So every time you have every time you're giving color to something that has a midpoint, it could be, for example, if you're thinking about in a completely different context, if you're thinking about the correlation coefficient R, right, of a regression, you can have positive numbers, you can have negative numbers. So if you're trying to show in a map your correlation coefficients across something and you have multiple of those, you could have your midpoint being 0, right? So everything that has a correlation greater than 0 is going to be, let's say, you know, purple in this case. Everything that's lower than that is going to be green in this case. So the midpoint just has to be a point that is like that has a clear midpoint distinction between low and high. In our case, yield by itself did not have a good midpoint just by itself, right? Because I cannot say that for every year yield of 1,000 is the midpoint. It doesn't make sense because sometimes 1,000 may be good, sometimes 1,000 may not be good depending on the year. So after we normalize it, now a midpoint of 100 means that is exactly that yield on that cell that's white is very close to the yield of the median, which is a midpoint of the statistical distribution. So that's why we chose 100. Does that make sense?
Yeah, I guess so, yeah.
Okay. Any other questions or thoughts about this? All right. So I do want to customize this plot very well, and then the others that come after would just copy and paste and do, you know, small modifications. So that's why I'm spending some time in this plot. Okay, next thing I want to do is I want to change some of the labels here. So I want to give a title to this map, and also I want this legend title that right now is SY17 because that's the name of the column. I want this to be something more informative. So if you recall, so let's add a plus here. If you recall, there is a function here that we use to change those types of things, and that function is called labs. So if you type labs, the first thing I want to change here or want to give here is a title. So it has an argument called title and open and close quotation marks. I just want to say 2017. So pretty straightforward. If you run it and you print it, now you have 2017 appearing on top. I also want to change the title of the legend because the legend is according to fill, and that's because of this, right? So we're changing the fill according to a variable, and that's what creates this legend. So we come here in labs, give it a comma, and it has an argument called fill. So what I wanna name this to is median standardized yield. If you just run it and then print it, you're gonna see this. So as is, this title here is kind of long, and I want to break line here before standardize and before yield, so it does not become a very long legend title. To do that, I don't know if you recall, but we just need to add the backward slash n. So I want to propose we add it after this dash, backward slash n, and then again after or right before yield. So backward slash n. This is the code for new line, so it breaks line. And this you can apply this to any of your axis labels, could be X, Y, any of those. All right, two last things. I want to change the theme, so I don't want to have the axis text here in this background. So let's change that at a plus and change it to theme underscore map. That makes things very clean, like we would want to have for a map. And then lastly, I want to change the legend position to be on the right side. So we add a plus, call the theme function. We have this argument called legend dot position equals to right. By doing all that, now we have this as our output. I just want to show you the code for another second in case you're still catching up.
I'll ask one more question, although you have told this before, but I just wanted to ask, can you differentiate between where we are using pipe and where we are using plus sign?
Yes, that's a great question, Kumar. So the pipe is what we use when we're doing mostly data wrangling, right? So the pipe is within data wrangling functions, which are like the mutate, select, filter, pivot wider, those types of functions, group by, summarize. The plus, we use plus when we are inside ggplot. So inside ggplot, so if you start a plot calling ggplot, then after that you use plus. Sometimes it could happen that you can do some data wrangling first with pipes and then feed that right into a ggplot, right? Which I think we may have done in a previous exercise, I don't quite remember. But what will happen then is within the wrangling steps is pipe, 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 pipe. Then the last pipe then goes into a ggplot, and after that point, it's just plus, plus, plus. So the ggplot here is what triggers the plus. It's just, yeah, a different syntax, but that's when we use each one of them.
Okay, thanks.
Okay, so before we wrap up, I just want to basically go through this for 2019, which is going to be very fast. I left you here empty. But we're basically doing the same steps as we did for 2017. So with that, instead of us typing everything again, I just want to invite you to come back to the chunk where we did that, which is the SY17. You can just copy, starting at the assignment symbol, you can just copy until that dplyr select until the end of that. So exactly what I'm showing you here, starting at the assignment symbol and finishing at the end of the select. And you can just copy that. Go back to your 2019, so SY 2019 and paste it. There are gonna be two differences we have to change, two things we have to change here. So the first one is the data set coming in. We need to change from yield 17 to yield 19. And remember, we do have a yield IC19 object, which was the one that we imported in the beginning of the exercise. And then once we select SY, I do want to rename that to SY19 instead of 17. So those are the only two things that we're doing here. And just to quickly walk you through, we're bringing yield 19, again, calculating the median for the 19-year only, standardizing again, rounding it, selecting the standardized value, renaming it to SY19 and the geometry only. So if you run it, it should run smoothly. And if you print it, you should again have a very similar object, but now called SY19. Then if you go to the next chunk, I already left all that chunk for you. So we're basically doing the same thing as before. So bringing GeoMSF, plotting the SY19 where the fill is equal to the SY19 value. We're using the scale fill gradient again with the same values, same breaks. I'm adding a title here called 2019, using the theme map to clear things up. And the only difference is the legend, I'm removing the legend. Instead of moving to the right, I'm just completely removing it. So if you just go ahead and run this and you print it, this is what you should see. The reason why I completely removed this, the legend here is because in the end, we're going to be combining all three maps. And so we don't have to have the same legend for all of them because now they're on the same scale. The legend should be applicable to all of them, the same legend. Okay, I think we can stop here. I'm going to take your attendance on GitHub.
Can you leave it in the last chunk for 17, please? For a sec. Thank you.
You mean this one here?
Yeah, for 17.
For 17?
That's, yeah, when you finish your right there. Go back. Right there. Thank you.
Let me see if I can do both things at the same time. All right, so I just submitted the issue. Make sure to claim your attendance while you're still in class. And then after that, we can stop here for today. We're going to continue and finish this exercise on Wednesday and go from there. And don't forget to submit your assignment 7 by tonight, 11:59 p.m. I guess, Kumar, your question about talking if, on question 2 of the assignment, we just went through that conversation when we talked about standardizing by the creating a continuous or categorical variable. So that was a discussion that we needed to have for you all to be able to answer question 2. So now you should be good. If anyone has any questions, I'll stick around for another moment. And if not, I'll see you on Wednesday.
Thank you.
Yeah. All right. Thanks, everyone.